Hello everyone. So in this video of chapter electrochemistry, I'll be talking about molar conductivity. Molar conductivity is represented by symbol lambda. The electrolytic conductivity is not suitable for comparing the conductivities of different solutions. The conductivities of a solution depending upon the number of ions present in unit volume of a solution. The solution which are having high number of ions or having high concentration, they used to have higher conductivity than the solution which are having lower concentration or low number of ions. So, if we are comparing conductivities of two different solutions, we should take same concentration of two different solutions. In 1880, German physicist Roche introduced a term molar conductivity denoted by lambda. Molar conductivity of electrolytic solution is the electrolytic conductivity divided by its concentration. That means lambda is equal to K upon C. SI unit of K is Siemens per meter and the SI unit of lambda would be Siemens meter square per mole. Now, what is the significance of molar conductivity? To understand the significance of lambda, let's suppose the volume of solution containing 1 mole of dissolved electrolyte. Suppose the solution is placed between two parallel electrodes which are having distance between 1 centimeter apart and the large enough to accommodate it. The electrical conductance exhibited by the solution is molar conductivity. Now, molar conductivity is the electrical conductance generated by all the ions in 1 mole of electrolyte. Now, let's talk about the relation between K and lambda. Conductivity K is electrical conductance of 1 centimeter cube of solution. If V is the volume of solution in centimeter cube containing 1 mole of dissolved electrolyte, its electrical conductance is lambda. Hence, the total conductance V centimeter cube is kV, which is molar conductivity. So, we can say here lambda is equal to K multiplied by V. And concentration we know it is C mole per liter. So, we can say here mole C upon 1000 would be mole per centimeter cube. We are transforming liter to centimeter cube. So, volume V of the solution in centimeter cube containing 1 mole of electrolyte is reciprocal of the concentration. So, we can say here V is equal to 1000 upon C centimeter cube per mole, or we can say here lambda would be equal to 1000 K upon C. This is the relationship between the lambda and concentration. Now, variation of conductivity with concentration. The electrolytic conductivity is electrical conductance of unit volume of solution. Depends on the number of current carrying ions present in unit volume of solution. This is what we have learnt. And on dilution, total number of ions increases, which increase the degree of dissociation also. And an increase in total number of ions is not proportional to dilution. Therefore, we can say here the number of ions per unit volume in solution decreases. This results in the decrease of conductivity with decrease in concentration of solution. Now, variation of molar conductivity with concentration. The molar conductivity with concentration, I can say here first, molar conductivity is the electrical conductance of 1 mole of electrolyte in a given volume, and the increasing number of ions produced in solution by 1 mole of electrolyte lead to increased molar conductivity. The variation of molar conductivity with concentration in case of strong electrolytes and weak electrolytes are totally different. We have to look at them in the different perspective, with the different perspectives. Now, strong electrolytes. The molar conductivity of solution having strong electrolytes increase rapidly when we are increasing dilution. It approaches to its limiting value when the solution is 0.001 molar or 0.0001 molar. The dilution has no effect on molar conductivity thereafter. The maximum limiting value of molar conductivity is the molar conductivity at zero concentration or at infinite dilution, and it is denoted by lambda naught. The zero concentration or infinite dilution means the solution is so dilute that further there is no increase in the molar conductivity. 19th century, Kohlrausch repeatedly did the experiments and show that molar conductivity of strong electrolytes varies linearly with the square root of concentration as. In this way, he has shown the graph in between the molar conductivity and square root of concentration. And he has given one relationship, which is lambda is equal to lambda naught minus A under root C. A is constant here, and for strong electrolyte, we are seeing the graph we are obtaining is linear. And after extrapolating this linear line, we are getting the limiting value of molar conductivity. But for weak electrolytes, molar conductivity of weak electrolytes increases rapidly on dilution. For concentration of 0.001 m or 0.0001 m, 0.0001 m. So I was saying, for concentration of 0.001 m or 0.0001 m, the lambda value is lower than that of lambda naught, the molar conductivity at zero concentration. And if we are plotting graph like we have plot for strong electrolyte, we used to get curvy graph, right? So the molar conductivity of strong electrolyte at zero concentration can be determined by extrapolation of the linear part, but this method cannot be used for weak electrolytes. Since we are not getting the linear graph, we used to get the curvy graph. So in that case, Kohlrausch law is useful for calculating lambda naught for weak electrolytes. Now we need to learn the Kohlrausch law and how the value of lambda naught would be obtained by Kohlrausch law. Kohlrausch law. Its law is the law of independent migration of ions. The law states that at infinite dilution, each ion migrates independent of co-ion and contributes to total molar conductivity of electrolyte irrespective of the nature of other ion to which it is bonded or associated. He has given expression like lambda naught is equal to n number of ions of cations, its molar conductivity, that is lambda naught of cation, plus number of anions and molar conductivity of anions. Both cations and anion contribute to molar conductivity of electrolyte at zero concentration. So lambda naught is the sum of molar conductivity of cation and that of anion at zero concentration, where lambda plus and lambda minus are the molar conductivities of cations and anions respectively, and n plus and n minus are the number of moles of cations and anions in a given formula of electrolyte. Now, application of Kohlrausch theory. The theory is used to calculate molar conductivity of electrolyte at zero concentration. For example, if I need to calculate lambda naught for KCl, so I will be taking molar conductivity of potassium and molar conductivity of chlorine. Since moles of potassium ion and chloride ion here is 1 so the formula would be like this. But if I am talking about barium hydroxide is producing one barium ion, two hydroxide ions. So there is 1 mole of barium and there are 2 moles of hydroxide ions. In this way I will be calculating lambda naught for barium hydroxide. The theory is practically useful for calculating lambda naught value for weak electrolyte from those of strong electrolyte. For example, lambda naught of acetic acid would be calculated by knowing the value of HCl, NaCl and sodium acetate. How? We will take lambda naught values of H and Cl, it is strong, we will get easily. We will take lambda naught value of acetate ion and sodium ion from the salt sodium acetate and we will subtracting the lambda naught value of NaCl. In this way, we will elaborate the cations and anions values of each ion in the given formula and finally we will be getting lambda naught H plus lambda naught acetate ion to give us lambda naught value of acetic acid. So in this way, by taking the values from strong electrolyte or molar conductivity's value I am talking about, we can calculate the weaker ones also.